Hi everyone, my name is Anand and I'm a senior product manager on the Amazon EFS service team. And today I'm going to talk about how you can modernize your applications that run on serverless and containers using persistent storage with Amazon EFS. So in today's session, I'll quickly talk about why you need to modernize your applications, how persistent storage and Amazon EFS fits into that modernization paradigm. Then I'll go through some getting started with EFS and containers and Lambda, and also show you a demo there. And we'll end with some best practices. So let's start with modernization. So the three main reasons why we see customers building and deploying applications using containers and serverless are to save costs, increase agility, and deploy and develop applications faster. So the first thing to save cost is that customers running applications on premises in their own data centers, for example, typically have to pay for a lot more infrastructure than what they use because they have to dedicate servers to single applications for security or isolation. And so most of the servers end up being underutilized, or they have to provision compute and storage ahead of time based on some sort of forecast, which usually means that, again, a lot of that infrastructure lies underutilized. The second is most applications have peaks and valleys of usage, so which means again you end up over provisioning or under provisioning your storage. And finally, companies or customers that adopt modern container and serverless services build their application development processes around them. So, which means it allows them to drastically decrease the time to market, uh, innovate faster, and deploy their applications to their consumers quicker, and thereby iterating much more faster and delivering business value more quickly. So, if you think about the modernization paradigm, if you start at the very bottom with EC2, where you have access to all the knobs you want to manage, or at the other end where you can go completely serverless with AWS Lambda and Fargate, where you're completely focusing just on your application and business logic. And so the layers of abstractions available to you with AWS is very empowering because your teams have the choice to pick the layer of abstraction they're most comfortable with. And we provide you the tools, services, and APIs that are necessary to help build your application. So let's start with EFS, and then we'll show you how it all comes together. Right? So we launched EFS in 2016 to give customers a super simple set and forget, fully managed cloud native file system, and you can get up and running in just seconds in as little as 2 clicks. So EFS is completely elastic. It automatically scales up and down as you add or remove files, and you only pay for what you use. Your performance automatically scales with your capacity, which, by the way, EFS file systems scale to petabytes in size. EFS is also highly available and designed to be highly durable. We offer a 4 nines availability SLA, and we are designed for 11 nines of data durability. To achieve these levels of availability and durability, all the files and directories are redundantly stored across multiple availability zones or AZs. And so EFS file systems can withstand the full loss of a single availability zone while still providing the same quality of service in the other availability zones. EFS is completely serverless. You don't need to provision or manage any infrastructure or capacity. And as your workload or application scales up, so does your file system, automatically accommodating any additional storage or capacity that's needed. In terms of connections, EFS supports up to tens of thousands of concurrent clients, no matter what compute type. So these could be traditional EC2 instances, it could be containers running on your self-managed clusters or on any one of the AWS container services, ECS, EKS, and Fargate, or they could be Lambda functions. You can also access your file system from on-premises if you choose to do so using AWS Direct Connect and AWS VPN. In terms of performance, EFS provides low, consistent latencies, single-digit millisecond range, and can scale up to tens of gigabytes per second of throughput and support over 500,000 IOPS. And we'll talk about performance a little later as well. In terms of storage classes, EFS also provides automatic cost optimization, where infrequently accessed files automatically move to a lower cost storage tier, saving you up to 92%. So let's talk about the overall benefits of ECS and EFS of containers and serverless with EFS, right? So kind of bringing it all together. So in addition to simplicity and security, there are other benefits. So let's start with availability and durability. Uh, both EFS and the compute services are regional services, so which means they run across all of the availability zones in a region. So you can build your application to be architected across multiple AZs, and they can share data as if they're local to each other. In terms of elasticity, it's obviously no surprise that the various compute services in EFS are completely elastic. So, which means as your application needs to scale out, the combination of services instantly provides additional compute and storage capacity. So, which means you can only focus on your application and business logic, and the compute and storage infrastructure in tandem just work for you behind the scenes, right? So you never have to worry about forecasting, over provisioning, under provisioning, or any of that. From a simple perspective, again, if you use, for example, serverless or Fargate, you essentially have serverless compute with serverless storage and EFS. So think about how powerful that is. And from a security perspective, we'll talk about that a little later. But you really have the full gamut or of IAM and EFS access points where you can have application specific entry points, and you can enforce file system permission so that when multiple applications access the same file system. And we'll talk about that a little later. So when you talk about application modernization, so there are two paradigms there, approaches. One is application migration, and there's application augmentation. So when you talk about application migration, so think about things like web or API serving using content management systems, where you want to modernize your websites or your digital experiences to run from, let's say, on premises or EC2 instances on containers or serverless, so that they can scale better, iterate faster, and all the other reasons that we talked about. Or for example, analytics or developer tools, where, let's say, you're building CI/CD pipelines on container services, for example, right? Or or on the right side, as we talked about, there's application augmentation, where you can have data pipelines that span both containers and serverless as well, right? So there are various application modernization. So there's migration, and there's building cloud native applications as well. So many customers are migrating existing applications from on-premises or EC2 instances into containers and serverless to simplify the operations, lower their compute costs, and scale more elasticity. With EFS integrations with ECS, EKS, and Fargate, applications that need shared or persistent storage can be easily migrated, and you can take advantage of serverless storage that scales elastically, so to speak, with your application. So, as companies containerize more of their applications, they often find that applications require persistent storage. So this is because applications are long running, they need to persist state for high availability, or because an application wants to scale out around a shared data set. So, for example, developer tools like Jira and content management systems like WordPress and Drupal use persistent storage to achieve high availability through an active standby model, often across AWS availability zones. Right. With machine learning, customers use EFS to store shared data sets and data scientist home directories, allowing them to uh, train models in parallel across multiple containers and access data from individual data science notebook containers. So as you can see, there's a wide variety of use cases or applications that really need persistent storage, even if when you build them on containers or on serverless. So next, let's talk about some real life customers who have actually uh, integrated or built their applications around EFS and some of the modern compute services. So Acquia is a customer that has a Drupal based platform, and they build digital experiences for their customers. And so what they did was they migrated and their Drupal based platform to run completely on EFS. And what they found was they were now able to drastically reduce their TCO through improved storage and compute utilization. They were easily able to scale to meet their customer requirements. as let's say they built websites for their customers, and then if the peak user load, they could automatically scale to meet those demands while still reducing their overall TCO and utilization. And more importantly, completely hands off, right? Remember the set and forget. It reduced their operational and administrative burden completely, and they did this by running the application on EKS and EFS. Another customer, Federated Wireless, used ECS and EFS to dynamically scale their Spectrum Access System platform that calculates path losses for all of the registered devices that they have. And they ran this in combination with ECS containers on EC2 spot instances so that they could reduce costs. And they found that by doing this, they decreased their execution times for tasks by more than 30%. Right, so a combination of cost savings with ECS, EC2 spot instances, and EFS, as well as much significantly reduced execution times. So let's talk about Lambda, right? So many customers are migrating existing applications from on-premises or EC2 instances to simplify their operations, lower their compute costs. And so what they do is they can now modernize their applications by sharing the same data, whether it's on EC2 instances or on a Lambda function on the same EFS file system. So let's talk about a common architecture pattern with machine learning inference. So it's a common use case, and inference is the real time part of machine learning, right? Once you use historical data to build a machine learning model, you want that model to classify or predict new users or events, and that's called inference. Lambda is very attractive for inference because it's completely elastic, which means you aren't paying if you aren't serving any predictions, and when you are making those predictions, you're only paying per prediction, right? So historically, the problem has been that deploying an application that does machine learning inference requires a lot of storage, and storage to hold the machine learning model file, storage to hold the code that interprets the model, and it's usually too large for Lambda to handle, right? Because of the temporary storage limits. With EFS, there is literally no size limit, and so you essentially get unlimited storage for your file system. So customers can use Lambda for any kind of inference use case. And only EFS can do this because the programming languages and ML libraries need this data to be available through a file API, which EFS provides. So an example of this is Surian, and they use Lambda and EFS to do sentiment analysis. So when support calls come into their call centers or contact centers, as soon as the calls are over, they perform a real-time analysis of the customer experience to understand what the customer sentiment was, and then perform any follow-on actions. And so what they need is the ML inference infrastructure that understands the sentiment to scale elastically with call volume. And so they were able to do that with EFS, providing a combination of high concurrency. Let's say you have thousands of calls coming in at any time, and they were able to do it very quickly with very low latency so that they can quickly make those sentiment predictions. And so another common category or use case that we see for EFS and Lambda is data pipelines or applications that help bring new data into organizations. So when you build a data pipeline with Lambda, you create multiple Lambda functions where each represents a processing step between raw data and data ready for use. And you need a way to kind of move data between these steps. Often the data that you need to pass is larger than the local storage limit of a Lambda function, which is 512 MB. So you need storage that can be natively used by your Lambda code, but doesn't have a size limit. So that's where EFS comes in. As a shared file system, you can configure each Lambda function to connect to a shared EFS file system, starting by reading data from the file system and finishing it by writing it back. So the data in this case can vary. It could be images coming from satellites, it could be uploads to your website, or it could be sales data coming from suppliers. In all of those cases, you want to make sure that your data pipeline starts working right away so that you can scan for viruses, do any sort of analysis, and reformat those resources or images into something that your business applications can use. And so with EFS and Lambda, you can build applications that do all of this in real time, paying only for what you use and without having to manage any of the underlying infrastructure. So think about how powerful that is. So again, a customer that uses this is Skywatch, which processes satellite images using Lambda and EFS. And so what they do is they ingest a large number of satellite images, and they have their own platform where they turn raw image data into tiles through a series of Lambda invocations, and then finally, once those processed images are done, they share it to their own customers, right? So they do a lot of processing with these millions of satellite images, and so they're able to concurrently process this shared data with significantly low latency. Another example is downstream. So downstream helps companies advertise or list products on Amazon.com to manage their sales and marketing. They continuously pull sales and advertising data from Amazon's APIs and process it with EFS and Lambda before presenting their findings with customers. So again, requires that very high concurrency and low latency and the scale as they make more calls. So with this, let's talk about how you can get started. So when you think about getting started, there's security and identity, there's performance and optimization, cost, and then data protection. So let's talk about security and identity first. So the two main goals that you, from a security and identity perspective, when you think about Lambda and containers with EFS, is that file systems should only be mountable by the applications that need them, right? So you don't want any sort of application to be mounting a file system. And second is applications that mount the file system should only have access to the data that they need. Obviously, you don't want multiple applications that access the same file system to be able to see or access data that from other applications, right? So you want that clear separation of data within this shared file system. And so let's talk about using IAM to authorize, let's say, your ECS task to access your file system. So this is really easy to set up. You'll first give your task an IAM role and then click the box to use that role to authorize with EFS. So EFS, if you don't check the box, EFS will treat your task as anonymous. On the EFS side, you can use an identity policy or resource policy. So in this example that you see on the screen, I have an identity policy attached to my role that gives full access to this particular file system. I also have a resource policy that gives full access to a particular IAM role. And obviously, standard IAM rules apply. A deny in any place blocks access, and at least one allow is needed to grant it. So let's talk about handling authorization using IAM. So there are kind of 3 degrees of authorization with the EFS. First is client mount, which allows a client to mount a file system but not write any data or perform any operations as root. When you do client write, you can read and write as any user except root, with root operation squashed to a reserved UID. And at last, you can add client root access, which lets you read and write to all users, including root. So let's talk about understanding container identity, right? So the main thing when you think about container identity is by default, the POSIX identity comes from the container image and not the task or the pod runtime. So what that means is if somebody within your team has, let's say, built an Nginx application, and they hand it over to you, and then you deploy it, the identity comes from the image, right, and not at build time. So that's not something that you want, because then you would have access that you ideally wouldn't want. If you think about it from a Lambda perspective, Lambda functions by definition have no predetermined identity, right? So if you need to access applications within a file system, you need to have some sort of a mapping to your file system identity. So this is where Amazon EFS access points kind of comes in. So let's talk about managing application identities with EFS, such as when you're sharing a file system with multiple users. So with containers, like I said, the identity is typically decided at build time and built into the container image. And so it isn't uncommon for applications to run as root, which means they will be trying to do all the file system operations as root, or be running as whatever user and group made sense to the developer who built it, right? Which may or may not make sense to the file system. So with access points, you get you give your application an entry point into the file system where all applications are overwritten to the UID or GID defined in the access point. So you know how it makes sense in the context of the data. So even better, access points can route your application in a specific directory. So your applications don't need to worry too much about which directory to CD into to get data, right? And even best, it creates that directory for you. So you don't need to set up permissions anywhere else like EC2 instance. So how do Amazon EFS access points actually work? So in this example that you see on your screen, you've deployed a container with a task role called app role. In your file system resource policy, you've stated that this role is only allowed to mount to your file system via a specific access point, and that's the access point that it's used to mount. So now this app has been built to run as root. So ordinarily, all our operations would be interpreted as root on the file system, which isn't always the best idea, right? However, because you're using an access point, that access point has placed the app in a home directory called /apps/my app, which is a path that you see on the screen, and is rewriting all the file operations to user ID group ID 123. So you can be sure that it has exactly the access to the data that it needs, no more and no less. So before I get into talking about EFS and getting started and with the ECS, EKS, and Lambda, a couple of common questions that usually come up is, hey, we talked about EFS and the containers in Lambda, but what is the advantage or when should I use EFS versus S3 and EBS? So because these are the three storage services that you have within the storage portfolios. With EBS, there are two considerations that you need to keep in mind. So the first is API and the degree to which you want to share the data. So with EBS, as many of you know, or elastic block storage, is single attached block storage. So it works well for cases when you have a piece of storage that's specific to a specific instance of an application, such as a specific container or EC2 instance. But if you need to share data between multiple resources, then you need a shared file system that kind of pushes you to EFS. Another reason why you might choose EFS over EBS is because of the regional nature of EFS that I just mentioned, right? It's a regional service. So if you want an application that can fail over from one availability zone to the other, then EFS is is probably a good fit. From a performance perspective, between EFS and EBS, there are three attributes from performance if you think about it, right? So there's throughput, IOPS, and latency. So between IOPS and throughput, there's fairly comparable between EBS and EFS. So out of the box, EFS gives you 35,000 read IOPS and 7K write IOPS. So from a throughput perspective, you can get up to 1 gigabyte per second, 3 gigabytes per second of read throughput, right? The only difference is in terms of latency. So latency is every time you do an operation, how long does it take for the operation to return from the storage? And so there's a difference from a latency perspective because EBS is a service where all of your data is held in a single availability zone, whereas as I mentioned with EFS, you write it to multiple availability zones. So which means there are more transactions going on behind the scenes. So this means that EFS does low single-digit millisecond latency and EBS does sub-millisecond latency. So most of the time, this really doesn't matter. If you're reading and writing big files, you aren't really going to notice this latency. But if you're running, let's say, a relational database use case where you're doing frequent transactions with small IOs, that might be one case where EBS is a better choice simply because of you need that low amount of latency. The next thing is around EFS and S3, right? So there are two reasons why you choose EFS or S3, and that's API and the access pattern, right? So by API, what I mean is if you're modernizing an existing application, remember that we talked about modernizing an existing application, and if that app already opens files, reads files, writes files, closes files, then migrating to EFS is much easier than rewriting to an object interface, right? So you don't want to rewrite your application to speak object when you can quickly migrate it to EFS. For access patterns, with S3, if you use S3, you have to download or import your files. So an ML model every time, right? So you have to build your logic to see whether your S3 object has not changed. With EFS, this is natively available. EFS also provides caching under the hood, so you'll get much lower latencies. And so additionally with EFS, for files that are constantly accessed, you do not pay for data access on EFS storage. You only pay for your underlying storage. So if you have a very read intensive application, it might end up being a little more cost effective for your workload if you're doing a large amount of read and writes, because you're not going to be paying for that on EFS. So let's come back to, now that we have covered EFS versus EBS and S3, let's come back to getting started. Right. So with ECS, we've made it super simple for customers to get started. So you can mount an EFS file system and point inside an ECS task, and the ECS task can run on EC2 instance or on Fargate depending on the launch type that you've chosen. The cool thing is that there's nothing you need to configure at an infrastructure level. Right? The integration works directly between the ECS task and the EFS file system by using the new EFS volume configuration directive inside the task definition. So if you go to your ECS task definition, you'll see an EFS volume configuration directive. You just have to update that. And the services natively map an EFS file system and point transparently without further infrastructure configurations. Right? Or if you're directly using the console, all you need to do is just select your file system ID and within your task definition. There's the EFS volume configuration. So let's go to EKS. So storage in Kubernetes is a little more involved. And so there are abstractions between the storage services and Kubernetes, as well as between Kubernetes administrators and developer users. So for those of you who are not into Kubernetes, so let's go into some definitions, right? So the first thing is CSI. So CSI, or the Container Storage Interface, is an industry standard. It's an industry standard way of connecting storage to containers. It's supported by Kubernetes as well as other container frameworks. AWS has developed CSI drivers for EFS, which we'll talk about today. The whole point of this is once you have the driver installed, you have a consistent way of allocating and managing storage no matter what service is providing it. The EFS CSI driver is completely open source and it's available on GitHub as well. Next, you have storage classes and persistent volumes, which are what Kubernetes administrators provision to provide storage to their users. So first, you create a storage class which describes a particular type of storage a user can request. So examples might be having one storage class for block, another for file, and you might have one for high throughput file, standard throughput file, and so on. Right? And within your storage classes, the administrator provisions persistent volumes or PVs, which map to actual units of storage on an EFS file system. So next, when a developer wants to deploy their application and needs storage, they create a persistent volume claim under a storage class and are allocated a persistent volume. So the user-facing object is called a PVC, or a persistent volume claim, since the user doesn't have or need visibility into how exactly their request was satisfied. Before you get started with configuring your persistent volumes, you need to install the driver. So if you're using EKS on EC2, it's just one command to install. So this will trigger a download of the CSI driver from an ECR repository and run it as a daemon set across your worker nodes. If you're using EKS on Fargate, you do nothing, right? We take care of it for you under the hood when we see that you're trying to run a task that needs EFS. So we recently announced dynamic provisioning, and the reason we did that was our customers were telling us that there was a lot of work to set up to initially provision their cluster and create persistent volumes. And so they wanted the Kubernetes CSI driver, the EFS CSI driver, to do that for them. And that's what dynamic provisioning does. So with dynamic provisioning, you create a storage class that points to an EFS file system, and when users create persistent volume claims, instead of being allocated something that you already had to create, the driver will go to the file system, create an access point in that file system, map that to a dynamically created persistent volume, and then give it to the user, right? So you have completely taken away all of the provisioning steps needed to get up and running. So significantly reduces the time to get started. EFS CSI driver, as I said, was open source. So the GitHub repo has several examples of how to configure storage. So has several examples of how to configure storage. So I encourage you to go there for reference, but we'll walk through a simple example here. So here we'll start by configuring a storage class. You'll see that there isn't much we need to configure here. Just tell it that it's for EFS, and if you want TLS encryption to be used for the mounts. Next, a persistent volume is created linking to the storage class, and this is where you specify the details about what file system it is and what path to mount. Next, the developer comes along and creates a persistent volume claim, or a PVC, against the storage class that we just talked about, right? You'll see that they request a specific amount of storage, which is important for storage systems that provision an exact amount of space with each volume. But since EFS is elastic, this value is pretty much meaningless. And last, the part that I've highlighted, they launch their pod referencing the volume claim and specify where to mount it into the container. And that's it. So finally, let's talk about Lambda. So with Lambda, it's super simple. when you have your Lambda system, you have your Lambda function configuration. You can attach your file system there pretty much easily, and then you also select your file system, choose your access point, and you select the local mount path. So next, let me just quickly show you a demo of how this kind of comes together. So let's start. Let's continue with the demo. So the first thing that I will do is walk through the file and file system creation. I already have one, but we're going to pretend that we're creating a new one. So I'll click on create file system. So for most cases, creating file system is as simple as just providing, let's say I provide a file system name, and then I just click the orange button, right? I also so first I provide the name and then I choose which VPC. And as I mentioned, so we have a regional and a one zone service file system as well. And so if you're wondering why you would choose a one zone file system when regional is available, it primarily comes down to cost, right? So a one zone file system is 47% lower than the regional offering. So for a lot of cases where you're developing applications or have kind of dev test environments, one zone might be a good choice. But for this case, I'm going to leave it at default regional uh, and create it, right? So let's assume that it's already created. So let's go to, let's say, a modern file system here. So first thing I'll quickly show you is the network. So if you go to the network tab, you see a bunch of things called mount targets. So think of mount targets as the windows into the file system or from each availability zone that you're in. So in this case, you can see that I'm in US East 1. So there are 6 availability zones there. So I'm going to have 6 mount targets. So if there's an application running in a particular availability zone, this is, let's say, in US East 1A, that's a mount target I'm going to use. If I'm in this availability zone, then this is the mount target this is the mount target I'm going to use. And the data the data is the same behind all of these because the file system itself is regional, right? So these are just the ways that you can kind of get into it from each availability zone. All right, so the first thing that I will do is I'll also show you access points. So remember I talked about access points. So in this case, for example, I have one access point that says it's my app one. So this access point is mapped to this particular path on my file system, and it's set with the user ID and group ID as 1000 and south 1000. So I'll quickly show you ECS first. So if I go to the ECS console, I'll just quickly show you how easy it is. So if I go to my task definition here, so if I show you, scroll all the way here. So if I go to the task definition here, you have the EFS volume configuration. So it's as simple as just providing a file system ID, your access point if you need it, and whether you need encryption, TLS encryption. So with that, I will quickly jump to Lambda. So I have a very simple Lambda function here. Or rather, let me just go back to Lambda and show you how it's all set up. So let's say I go to Lambda. So the first thing is you provide your Lambda function name. Let's say I provide modern file system, and and then you provide. So many of you might already be familiar with this. So one thing you want to do if you're creating a Lambda function is put it into a VPC. That's because EFS is available from within your VPC and it's not a public resource, right? So if you go back to your Lambda function here and go to configuration and go to file system and let's say edit here, uh, that's where you see that it's as easy as just mounting your file system here. So you have to use an access point, and the reason you have to use an access point is Lambda. As I said, Lambda does not in any other place expose what user ID or group ID or application is running as, because that's not a thing that serverless developers usually think about, right? So by putting an access point, that's where the identity kind of comes in. And when I say mount slash EFS, that means that any file that I write within this path is going to be going to dash EFS, and really that's it. So let me kind of run to the application that I have. So this is a very simple possible prototype of a search engine on EFS. So there's a search file that's stored on EFS, and that's where I'm mounting my file system to. So the file, this is the file within the path that I'm going to be searching against, right? And I have an API uh, that I've linked using API gateway, which is going to trigger the Lambda function that exposes this function to the world. So let's say, for example, that I run a simple, I call this API here like this, and it says Lambda, and it says, let's say, found true, right? So let me show you what that might actually look like. So if I connect my file system here, I can actually show you what that looks like. So it has a word Lambda. So let's search for on the same API. Let me now search for the word India, for example. So you say it says false. So let's say I did I will did this, and let's say I did India. Oops, escape, and right. So then I've just quickly made a change to the file, and let's say and I run it now. It's just found true. So it's almost instantaneous. And so if you think about this at scale, then you're uh, then you can see how if you have machine learning models that are tens of gigabytes of size, or they're being, or let's say your multiple resources are sharing the file system, how quickly your how quickly changes or write to a file can be picked up by the other resources that are accessing the same file system or that are part of the same application. All right, so now that we'll just quickly wrap it up by talking about best practices. Now that we have discussed IAM and access points, and I showed you how to do all of that, I want to summarize with a few suggestions on how you should configure your environment. Unless, of course, you know better, first use access points. Even if you have just one app per file system, this takes guesswork of what user or group the application will run as and helps you avoid any file system permission setup. Next, use IAM as a primary way of authorizing tasks to your file system. Security groups are another way, but it's harder to reason about network level access than app level access. And lastly, just enable encryption. It's single click without any performance penalty. Let's talk about performance. So for those who not have seen this, we recently announced a big increase to the number of IOPS you can drive. We also tripled read throughput that you need for your application. So, for example, with machine learning inference sort of workloads as well. So, we have made a lot of improvements from a performance standpoint that will really help you as you build your applications on containers and serverless. Uh, from a best practices perspective, the first is we generally recommend to use the general purpose file system mode when you create a file system. Configure provision throughput for initial need. So as your file system grows, you will eventually be given higher throughput. Set up CloudWatch, Amazon CloudWatch, so you can continuously measure metrics such as your throughput, IOPS, and burst credits as well. One of the other interesting thing that we have with EFS is also infrequently accessed in the infrequent access tier, where files that where you can set up lifecycle management policies, where you can say if only 7 days. Uh, if a file has not been accessed for 7 days, move it to your infrequent access storage tier. And as you can see, it's significantly cheaper and it will save you a lot of money for files that are not being accessed. And you can do this automatically. And by doing this, you can effectively gain a storage cost of 8 cents per GB month. We also, like I mentioned when I showed you the demo, we have a regional, we have the regional service as well as the one zone storage class. So depending on whether you want your application to be regional and have across easy failovers, or if your application is just can run within a single zone, single availability zone. And finally, nobody wants to be in a situation where they accidentally delete or overwrite important application data, especially when it's so easy to avoid. So you can avoid it by configuring AWS backup to backup your file systems. So you can configure tag-based policies to configure all of your file system backups at once, along with rules on when to migrate data from warm storage tier to cold storage. So if you do need to restore data, you can either restore a whole file system or a single file or directory. So with that, I come to the end of the session. I hope this helped you understand how EFS as a persistent storage is really helpful to enable several use cases as you migrate or modernize or build new applications on container services or AWS Lambda. So I hope you start building using EFS and AWS container services and Lambda, and good luck with that. And thanks for your time.